Hey everyone, we are the Missouri S&T Rocket Design Team.
And we are the Multirotor Design Team.
This year we're going to be collaborating as the Advanced Aerial Vehicle Group 2.0 to participate in the Argonia Cup competition.
The changes made to the challenge are really cool and we're super excited to take our shot at conquering them.
Here's some of the changes we've made so far.
This year's competition added the requirement of building a two-stage rocket, which created challenges for us when designing and building. In previous years, we didn't start the building process until the beginning of the spring semester. This year, we decided to start building in the fall semester in order to have as much time as possible to build the extra parts needed for a two-stage rocket.
We also faced challenges with the electronics for the rocket. We have an additional electronics bay for the second motor, and we had to incorporate staging logic into our altimeters. This includes separating the stages and igniting the second motor. Another change to the competition is the scoring. Until this year, the score was calculated using only the payload's distance from the target. But this year, the rocket's altitude will also be a part of the score. We've designed the rocket to reach the highest possible altitude by reducing its diameter and reducing weight where possible.
This is our design for the rocket of unusual size. She is 137 inches tall with a 4-inch diameter and weighs 30.1 pounds. The airframe is fiberglass and epoxy was used to attach and reinforce the fins.
The booster section has an L1520 motor with a 3,769 Newton-second total impulse and a 2.49 second burn time. It has birch fins with a carbon fiber layup, and the electronics in the section handle the recovery of the booster. It has two altimeters, an RRC3 and Easy Mini, which ignite black powder charges that eject the parachutes.
This is the interstage coupler. It attaches the booster stage electronics to the sustainer. It has two intercouplers, the booster's electronics bay and the sustainer, which connects to the booster. It has black powder charges which will ignite and separate the booster section.
So this is the sustainer section of our rocket. It is equipped with a J415 motor with a total impulse of 1,291 Newton seconds. It also has a burn time of approximately 3.04 seconds. Now the fins on this stage are the same as the booster, being of birchwood with a carbon fiber overlay. Now the electronics for this section, which are run through metal rods through the centering rings, handle the stage separation as well as the sustainer ignition for the second engine. This also handles the recovery of this stage and the drone ejection.
This is the drone section, which holds the drone and ejects at apogee. It is attached to a bulkhead, and we use CO2 instead of black powder to prevent short-circuiting. It also holds the third electronics bay, which has an RRC3 and stratologger, and it handles the recovery of the drone.
The first stage of launch is the initial takeoff, where the booster motor will ignite and launch the rocket to about 5,000 feet. Once the booster motor burns out, the stages will separate and the booster section will begin its recovery deployment. Staging electronics will then check if it is okay to ignite the second stage. If all the conditions for staging are met, the sustainer motor will be ignited, which will carry the rocket all the way up to apogee. At apogee, the sustainer will separate into two sections, the drogue section and the motor section. At this point, both sections will deploy their drogue parachutes to begin a controlled descent. The drone will also be released from the rocket at apogee and will begin its piloted descent to the target. As both sections of the rocket approach 1,000 feet, the main parachutes in each section will deploy, allowing both sections to descend safely to the ground.
The rocket of unusual size is predicted to take 26.1 seconds to reach an apogee of about 11,300 feet. It reaches a maximum velocity of 871 feet per second and a maximum acceleration of 12 Gs. The total flight time to the rocket is 168 seconds.
This year at Argonia, we decided to reduce the rocket to a 4-inch diameter, and as a part of Multirotor, that puts us into a tighter constraint. As a result, our previous drone design wouldn't fit into the rocket anymore, so we needed to come up with something new. And that's where we get this, bone drum. Bone drone allows us to reduce the amount of movable parts and just make it into a stick. There's a flaw in its roll, but all other controls are pretty regular with any other type of drone. The main constraint is just getting proper PID tunes and doing a lot of tuning to make sure that the roll is accounted for so that when we eject, we'll actually be able to recover the drone properly.
So, I will start with the release mechanism on the back of Bone Drone here. So Bone Drone overall is 8 inches in length and 15 millimeters tall. The release mechanism is housed in the back, which will connect to the 15 millimeter steel standoffs. That will be 3D printed and house an SG90 tower servo that will release a 1.4 millimeter steel pin out of the back, so that can connect to a steel cable or an eye bolt or whatever it is that we're connecting to drop straight out of the rocket body. The frame is 3 millimeter carbon fiber, and directly inside of the frame houses the golf ball, just to cut out directly in the center, so the golf ball will be directly integrated into the frame. The motors are 2200 kV motors, which means they use a 4-cell power system, and for battery placement we will have a 2S battery on either side of the Bone Drone, and those are each 1400 milliampere batteries, so that comes out to 4S 1400 milliampere power. For the video system, we have a long-range HD video system, so the pilot will be able to see in real time and low latency 1080p footage to be able to navigate back to the drop zone.
See you in Kansas!